各位同学，我很高兴有机会跟大家讲一学期的大一物理。我在80年代、90年代在美国Stony Brook 大学也教过2次大一物理。我猜想你们的成绩会比 Stony Brook 的学生好得多。所以你们得当心，因为我预备教完了以后写一篇文章讨论Stony Brook 的学生跟清华的学生的对比，所以你们也可以说对于清华的名誉负一点责任。我刚才算了一下，是66年以前在昆明念过大一物理，那个可以说是我第一次接触到物理学。那么我希望在这一学期里头，大家不单学到一些物理，还学到一些微积分。这个微积分我要你们特别注意的是这本教科书 Halliday Resnick Walker 的 Appendix 1。这个 Appendix 1里边所讨论的一些公式我希望你们假如你们已经念过微积分，你就复习一下；假如你没有念过微积分，你要注意那些公式。But I also want you to learn some English. I understand some of you would be able to understand my English, but others may have some difficulties. I hope by speaking slowly you could understand most of what I say. But I want also to tell you a very good method to learn English. To learn English, you have to learn how to listen, how to read, how to speak, and how to write. Although those are very different, but there is one thing which ties them together, and that is your own pronunciation. For a Chinese student at the beginning, there's a tendency to be very much afraid to speak because the Chinese pronunciation and English pronunciation are very different. The Chinese language emphasizes the muscular movement of the mouth in the front, like the lips, the teeth, the tongue. In English, the main part of the vocal organs are more backwards. So you have to learn to move the center of attention when you speak from the front of the mouth to the back of the mouth. And how do you do that? There's no better way than to read aloud. So I want every one of you to spend maybe 3 or 4 minutes every day and read aloud. If you practice that for, let's say, for a month, I can guarantee your English would improve. Because, for example, English grammar has many peculiar features which are not understandable to a Chinese student. 我刚念英文的时候，觉得很奇怪，你 I am, you are, he is， 为什么要的更改？ 那么为什么要第三身？为什么多数要加 s？ 这个我当初念的时候，最初觉得这个很不自然，觉得这中国这个是比较自然。可是后来我懂了，它这个所以有这些加 s， 有些inclination， 它的原因是与发音有关系的。所以你如果发音发的好的话，很多文法上的问题 you would understand naturally. Therefore, to try to pronounce things correctly and aloud is very important. For example, you have in front of you this handout. Everybody has that. On the first page is an appendix. I'm going to add to this dictionary. I'm going to add to this dictionary later. But if you turn to the next page, the next few pages are from Feynman's book. So I'll give you an example. If you look at the first paragraph of this handout from Feynman, it's a very short paragraph. You can spend 2 minutes in the morning reading it aloud. In fact, preferably in front of a mirror, because then you can watch yourself. If you have a recorder, record it. After 1 month, you would realize, after 1 month of this practice, if you listen to what you had recorded a month ago, you would realize that you have improved. So this is an important thing. I want you to do this. In the latter pages, no, it's not in it's in the on the web. There is a syllabus, and you should download that syllabus and read that. That is what we are going to discuss in class. Now we go to chapter 1. Of the book, Halliday and Resnick, etc., etc. The chapter is very simple. It talks about the units, and I want you to learn the chain link rule. Every physical quantity has a dimension. It has a unit, except for numbers, for pure numbers. So if I say something is 1 meter long, it is not 1, it is 1 meter. So remember that the physical quantities have a dimension. It has a unit behind it. And the unit can be, you can calculate with the units. To give you an example, if you are asked how many seconds is there in 1 year, of course I'm sure you know this immediately, but I want you to do it in the following way, because that tells you how you can calculate with the units as if the unit is a number. So you would write 1 year is equal to 1 year divided by days. But once you have written that, you have to do this. This is correct, because these days too would cancel each other. But you can write the days divided by hours. You have to write this again. So these hours cancel each other, the days cancel each other. So it's an identity. But you can hours, you can have minutes. And you can write seconds. and write seconds. It's important that if you treat these units as if they were numbers, they cancel out correctly. Now you immediately know 1 year divided by this 1 year divided by day is 365. Days divided by hour is 24. Hour divided by minutes is 60. Minutes divided by second is 60. And you still have the second here. So now you know how many seconds. This is of course trivia, but what I want you to learn is that you must treat the units correctly, so that I think this explains to you how you treat the units correctly. And when you get to complicated problems in physics, you have to remember this rule. We are going to adopt the MKS system. MKS means meter, kilogram, second. When I was a freshman student, the internationally adopted system was called CGS. That is centimeter, gram, second. Which is, of course, deeply related to the MKS system. But something like 30 years ago or so, internationally, everybody now adopts the CGS system, the MKS system. An important concept that you must remember is the significant figures. This concept is extremely important for physicists and for all scientists. Namely, if I write 3.05, I want you to understand that that is not equal to 3.05. What is on the left side mathematically is equivalent to what is on the right side. But in physics, when I write 3.05, I mean it's between 3.04 and 3.06. When I write 3.0500, I mean it's 3.050 between 3.0501 and 3.0499. In other words, when you write a physical quantity down, the last figure has an uncertainty of plus minus 1. Therefore, these two numbers are approximately the same, but the number on the right is much more accurate than the number on the left. So these two are not identical in physics, although in mathematics they are the same. So that is called the significant figure. This one has significant figure up to the second decimal point. This has significant figures up to the fourth decimal point. I can write 3.05 of course, 3.05 is equal to 305 times 10 to the minus 2. In this case, both sides are equal mathematically and physics-wise, because the last figure has a possibility of plus minus 1, and they are, of course, equivalent. you should read in the book the discussion about the significant figures. I want you to remember about the velocity of light. Velocity of light is is 3.0 times 10 to the 8th meters per second. This is a very accurate figure and is universally used. But a more accurate one is given in the book. It is 2.99 You see that it has 1, 2, 3, 4, 5, 6, 7, 8, 9. Nine figures of accuracy. The reason that one can write such a number down is because in the last 30 years it has been able to measure both time and distance so very accurately. This is a very precise number. Does anybody have any difficulties understanding my English? No difficulties. Good. There's a question that we have to discuss now, namely, how is the second defined? In the early days, the definition of a second was using some sort of a clock. But of course, a clock, even a very accurate clock, is not accurate enough by modern standards. So now it is defined on page 6 of the book. In the middle of the book is the definition. I'll read it to you. 1 second is the time taken by 9,192,000. It's 9,192,631,770 oscillations of the light of a specified wavelength emitted by cesium-133 atom. In other words, it's defined in terms of that many periods of a specific emission from cesium. Cesium has many isotopes. Cesium-133 is one of them. And that isotope emits many lines. There's one specific line which has been chosen internationally. And that many 6 billion something oscillations is defined as 1 second. So it is a very precise definition. Actually, if you want to be even more accurate, you have to further define that cesium atom has to be in vacuum. If the cesium atom is under pressure, the period may be slightly different. So when you get to such great accuracies, you have to be very, very precise. So that is the definition of a second, of the unit of time. Now, how about the definition of the unit of length? For that, read page 5. In page 5, there is a statement which says the meter is the length of the path traveled by light in a vacuum during a time interval of that many of a second, that much of a second. This is now the international definition. The reason that there are these somewhat complicated definitions is because we now have the means to make very precise measurements. Originally, more than 100 years ago, when there was an international convention about the international units, the distance, the centimeter, was defined as the distance between two marks on a ruler kept somewhere in Paris. That you can see cannot be very accurate, because if you have a mark, if you have two marks, the most accurate you can imagine is maybe a fraction of a millimeter. As time goes on, one realizes that that is not accurate enough. So therefore, the definition was changed. It was changed several times, and now it reached what we just read. The time measurement is the most accurate. So therefore, first you define the unit of time. The distance measurement is the next accurate. So one defines it by saying the distance is related, the unit meter is related to the amount of to the length traveled by light during a certain time period. So therefore, what we have, what I want you to read is unit of time defined. How is the unit of time defined? Then unit of length. Then the unit of mass. I want to emphasize here that the unit of that mass is not equal to weight. In daily language, there is confusion. We say something is 1 kilogram. When in physics, when you say something is 1 kilogram, you mean its mass is 1 kilogram. It's it's related to the number of atoms and the mass of each atom added together, including the electrons, and that's the mass. So mass is a measurement of the bulk, while weight is a measurement of a force. When you say that you weigh 50 kilograms, it means that the Earth attracts you with a force which we define as 50 kilograms. So mass is a measurement of the bulk, while weight is a measurement of a force. These two are related but different concepts. We are going to have more to say about this after we get to discussing the 3 laws of Newton. Any questions about what we have said up to now? About the units, about significant figures, about actually about everything in chapter 1. By the way, there is in the book, near the end of every chapter, there's a section called Review and Summary. For you to test yourself, read that review and summary. If you understand everything in that section, you have captured the essence of that chapter. So while you are studying that chapter, refer to that section, and after you felt that you are finished with the chapter, read that section again to assure yourself that you have gotten everything that there is in that chapter. By the way, if you read the handout, read the syllabus page. It tells you what is the textbook. The textbook I shall refer to as the HRW. You must have that book. Then there are the reference books, Feynman Lectures, 美国物理试题与解答第一卷，跟赵凯华、罗卫因所写的新概念物理教程力学部门。不过这三本书the relevant chapters I'm going to Xerox and give to you. I will assign you a number of exercises, around 7 or 10 every week, and you must hand them in next Monday. If you are late in handing in the exercises, your grades for that week will be discounted. And there will be a midterm 期中考试, a final 期末考试, and your final grade would consist of 30% of your exercise results, 30% from the midterm, and 40% from the final. That page also lists the office hours of myself and Professors Ran Dong and An Yu. So, for example, for this week, if you read the syllabus, I want you to read the Halliday textbook, chapters 1 and 2. Also familiarize yourself with the useful appendices A to G. Familiarize yourself does not mean that you have to remember it. It's just that you know that there are these appendices, and at the proper moment you know where to find, for example, an accurate expression for the velocity of light, or for the Planck's constant, or for a specific formula giving you an integral. If you just flip through the pages and sort of scan appendices A to G, those are very useful information for you. And then the first week's exercises are listed underneath A, B, C, D up to H. And as I said, you should do these exercises and give them to me next Monday. Okay, no questions? Then we'll go to chapter 2. Chapter 2 talks about motion along a straight line. It's a one-dimensional motion. Now we all are familiar with some concepts. After all, we travel around, we move around, and we ride in cars. So there is the concept of an average velocity. What is the meaning of an average velocity? If you are traveling along a line, you go from here to here, there's a distance between them. Let's call that distance delta x. The distance divided by the time. Delta t is the time interval. Delta x is the distance. By the way, is this pen too thick? Is it better to use a thin one?这个不好，这个没有墨了。
用粗的还用细的？还用粗
的？这恐怕也是粗的。我要的是粗的，不过。
这是粗的。
这个好一点。So the distance traveled, the delta x, divided by the time interval of that motion, that is the average velocity. So this concept is elementary. Now, if I now take half of the time, so this is the average velocity during this interval. If I now say I only look at the same motion, but only look at this distance, then I get another average velocity. So you can have average velocity of this interval, this longer interval, or the average velocity in a shorter interval. If you now make that the interval shorter and shorter, you get when you go to zero distance, that velocity, average velocity is called instantaneous velocity. And that is what is important. So it is equal to limit of this average velocity as the interval goes to zero. If the motion has a uniform velocity, then it doesn't matter whether you take the average velocity of a long interval or a short interval. But if, for example, it's a curve that's accelerating, then the instantaneous velocity at the beginning is not the same as the instantaneous velocity later. So in general, the instantaneous velocity is not necessarily equal to the average velocity at any time. This quantity, when you take a ratio and go to the limit of infinitesimal intervals, that is a concept fundamental to differential calculus. And in differential calculus, one writes it as dx dt. If you have studied differential calculus, you would be familiar with this. If you have not, you will be learning it both here and in your calculus course within the next week or two. Does anybody know who invented the differential calculus? Differential calculus was invented by two people, Isaac Newton and Leibniz. Newton was born 1642. And Leibniz was born the birth of differential and integral calculus is a great event in the history of mankind. One of the reasons that the Chinese science, modern science, did not develop in China was because, for various reasons, differential calculus was never invented in China. Actually, after you have learned the differential and integral calculus, you will realize that it's the most elementary concept. It is the most natural concept. That is a general situation relating to many physical laws. Before you understand it, it may not be reachable. But after you understood it in a more precise manner, you realize that it is a very natural and very simple thing. And differential calculus is a very good example of that situation. Newton clearly used differential calculus to write his big book, and that book is universally regarded as the beginning of modern science. It's called Principia Mathematica. It was published in 1687. But a very strange thing happened. Although he clearly developed both differential and integral calculus, he did not use differential or integral calculus in his book. This is called derivative. Dx dt is called the derivative of x with respect to t. Derivative is导数. If you look at the dictionary I gave you, derivative is 导数. Dx dt is the derivative of x with respect to t. Newton, in his work leading to Principia Mathematica, clearly used differential and integral calculus. In fact, the book was, most of what was in the Principia was done 20 years before that. It was done in the year 1666. But it was delayed. The publication was delayed by 20 years, partly because he needs to prove the following. The Principia Mathematica produced a tremendous impact on mankind because it explained the planetary motion of all the planets around the sun and the motion of the moon around the earth. But in order to discuss, for example, the motion of the earth around the sun, he knew he had to deal with two spheres, a big sphere which is the sun, and a small sphere which is the earth. Now in his original calculation, he took the sun to be one point, a heavy point, and he took the earth to be a lighter point, but both of them are points, and one small point going around a heavier point. Then there's the question of, okay, but the sun is not a point, it's a sphere. So he had to prove that when you have universal gravitation, the universal gravitational force between a small sphere and a big sphere gives you a motion which is the same as if those two were just points. This requires an integral calculus, and it took him 20 years before he completely satisfied himself that that was correct. But the thing which is very strange is that when he wrote the Principia Mathematica, he did not use differential calculus. He did not use integral calculus. The whole of Principia was written in terms of a language similar to Euclid's geometry. I'm pretty sure in high school you have learned geometry, and that geometry follows the style of Euclid. You start with some axioms, then you have some propositions, then you have proofs, and you have corollaries, etc., etc. Newton patterned his big important book exactly like Euclid in this style. Not only this, he tried to prove everything as if it's a geometrical problem. Because of that, for the last 20 or 30 years, very few people have really plowed through the whole book. Everybody knows it's a most important book, but it's too complicated because if you do things with differential and integral calculus, it becomes very simple. But if you don't use that and do it geometrically, it becomes very complicated. The great astrophysicist Chandrasekhar was born around 1910, so he was some 10 or 11 years older than I am. In his old age, he decided to understand precisely the geometrical arguments of Newton in the Principia. Chandrasekhar was very proud of this book. I didn't read it, but if you are interested, you could go to the library. I'm sure the library has a copy of Chandrasekhar's modern interpretation of what Newton has done geometrically in the Principia. Leibniz was a German mathematician, and he was not so much a physicist like Newton was. He was more a pure mathematician. And it is now believed that he independently invented differential and integral calculus. But he had correspondence with Newton. So there was great controversy about whether their discoveries were independent or not independent. And that became one of the great scholarly debates around the end of the 17th century. In earlier centuries, before the 20th century, the biographers, all biographers, tend to only say good things about a famous name. For example, there were biographies of Newton, and in these biographies, Newton was a great man, and he was almost perfect. But in the 20th century, but by the way, that is more or less the kind of style of biographers in China in ancient times. But starting in the 20th century, there is a new movement of biographies in the West. There began a style in which one tries to paint the whole person. And now there are many biographies which show that Newton, though a great scientist, was not a likable man. He was not a kind person. He was vindictive, and he was not a person who was well liked. And the controversy between him and Leibniz was one of the things that dominated the end of his life. If you go to the library, you can browse through some of the books which give details of the life of Newton. Now, one of the controversies between Newton and Leibniz was what symbol to use for the derivative. dx dt is the derivative of x with respect to t. That is the notation of Leibniz. It was not the notation of Newton. Newton did not use the word derivative. Newton called it the fluxon. Today nobody uses the word fluxon, and the notation of Newton was very awkward, while this dx dt notation is very convenient. So today everybody uses Leibniz notation.是几点钟？他是不是也要响铃？
但是他这没响，他这个铃没响，可能坏了，我们可以休息一下。
Okay, so we'll have a 5-minute recess and then reconvene.